So for this talk, I thank you very much to the organizers for the kind invitation and to all the staff at IPAM for organizing both this workshop and the long program, which is absolutely wonderful. I'm Emily. I'm a PhD student in Lyon, working at the ENS with Daniel, who was at the ENS and is now in Copenhagen. This talk is based on a work we did about a year ago, generalizing the classical Wasserstein distances to generic order P. This, we have the archive link. It's published about a couple of weeks ago. I should add that if you have read this paper or skimmed over it, the version which is now on archive that was updated a couple of weeks ago is like significantly improved. So there is a new version. So in this work, as I said, we propose a definition of the hierarchy of quantum Wasserstein distances of order P based on an underlying distance on pure states. As a rough outline of the talk, I'll give you a little bit of an introduction to the classical setting. Obviously, those of you who've been here for longer than just this week will have heard this about 10 times, so bear with me. I'll try and explain or emphasize the parts that are most relevant to this context. And then I'll tell you what kind of motivated this novel definition, the key properties that we're trying to reproduce, and give you the definition of the distance we've introduced. I'll tell you what it looks like and what properties it satisfies, what it looks like in a few specific cases for specific underlying distances or underlying geometries on your Hilbert space, what you can do with it, and then we'll conclude by talking about where we go from here. So, as I said, the classical problem we're trying to generalize is the definition of the Wasserstein distances, which talk about the cost or the minimum cost needed to transport mass from one place to another. So classically, you would set yourself up with a measurable space, a cost function on that space, where C of xy represents the cost of transporting one unit of mass from point X to point Y, and two probability measures that you're trying to transport mu onto nu. And then we define a coupling as a measure on the product space, which agrees with mu and nu on the marginals. The way you would interpret this is just that we use gamma for a coupling, and then gamma A of A and B is just the amount of mass transported from set A to set B, or pointwise if you're thinking pointwise. So we know how much mass is transported from one point to another via this kind of gamma, which encodes instructions for how you should transport the mass of mu onto the mass of nu. We know how much it costs to transport mass from one point to another, and so the natural cost of transporting mass via the instructions provided by gamma is just the integral of the cost over gamma. And then optimizing over these couplings, which are instructions for how to transport the mass of mu onto the mass of nu, you get the minimum cost needed. The case that we most often care about classically for applications and general study is what happens when your cost comes from a metric. So when you equip your measurable space X with a metric, we can then take the cost. Do I have a little, beautiful. You can take the cost to be the pth power of your metric, which is kind of a natural thing you might choose as a cost. And this gives us the definition of the classical Wasserstein distances. So the Wasserstein distance of order P between two measures on a metric space is just the optimal transport cost with respect to the cost being the pth power of this distance, taking the pth root. These are the objects we're trying to generalize. Just to give you an idea of what this looks like, the kind of canonical example of this construction is I suppose the very simplest example is if you take a finite space, not necessarily finite, but simplest would be a finite space equipped with the discrete metric. And if you look at the classical Wasserstein distance of order 1 with respect to this discrete metric, you just recover the total variation distance. So that's what happens in the kind of simplest case. What was I going to say here? That's it. So why do we care about this in the quantum setting? Well, as a lot of people have talked about over the course of this week already, you can do a lot with the theory of classical optimal transport. Everything from kind of the obvious economical and logistical applications of like moving stuff from one place to another, to talk about concentration inequalities and mixing types of Markov chains, machine learning, chemistry, tons of different things. And we would hope that by generalizing these classical distances to distances on quantum states, we would be able to recover some of these applications, replacing probability measures with quantum states, hopefully to recover some very nice, for example, concentration inequalities about quantum states or mixing times of quantum Markov chains, things like that. And so it's a very kind of well-motivated problem to try and generalize these distances to the quantum setting. So I should add, we're obviously not the first to try and do this. In fact, there's been so much interest in this problem that there's now like a whole IPAM long program on it. But I'll talk a bit about what exactly this work brings in a moment. When we talk about what we'd want out of a quantum generalization of classical Wasserstein distances, there's a ton of different kind of desirable properties that we could hope for. The kind of obvious one is that this distance actually be a distance. Classically, the Wasserstein distances are all true metrics, and so we'd hope, particularly for recovery of some of the properties, some of the applications, that this would actually be a true distance. So we might hope for it to be non-negative and symmetric. We might hope for the triangle inequality to hold. Some other things which are useful in the classical setting is that as long as your distance d is not completely pathological, these things are continuous. An important kind of simple example is what happens again with that example I gave you about the discrete metric. So classically, first order quantum Wasserstein distance the first order classical Wasserstein distance of the discrete metric gives you the total variation distance. When we translate that to the quantum setting, we might hope that a first order quantum Wasserstein distance recovers the trace distance, which is just the quantum version of the classical total variation distance in a number of different ways. And we might also hope to recover data processing. I should add, we wouldn't generally expect, depending on the geometry underlying our system, we wouldn't generally expect data processing to hold for every channel. But for quantum channels which respect the geometry of the underlying system that we have applied, we would hope that you might be able to recover data processing for those channels. And then some other things we might hope for in the kind of practical setting. First of all, it would be nice if these things were easy to calculate, just for practical applications. If you don't actually know what your distance looks like, then it's kind of difficult to use it. A big one, the one that we're going to talk about here, is if you're trying to recover as many applications as possible, it's generally a good idea to have your distances defined as broadly as possible. So in particular, it could be very important that your distance be flexible in both the underlying geometry that you apply to your system and also the order p with respect to which you define it. And then, of course, the main aim is that we recover some of the classical applications of these distances. So, what would this look like if you just tried to do it naively? In a very naive generalization, you would, if you were to literally translate the classical definition into the quantum setting, you would end up with a Hilbert space, replacing your space X. You would end up with states replacing your probability measures, quantum states, and you would end up with a cost matrix, which is either the pth power of some distance matrix, or C, a cost matrix which generally has a kind of pth order flavor. What I mean by that is, for example, a cost matrix which is defined as a sum of squares would have a second order flavor, something like that. And so if you literally just translate the classical definition into the quantum setting, you end up with a definition of a quantum Wasserstein distance where you just literally take the infimum over all states on the product space whose marginals agree with the state you're trying to transport, and you take the equivalent of the integral, so the partial trace of the cost times the coupling. Unfortunately, this kind of naive generalization comes across a lot of barriers. In particular, it's been shown that no cost matrix actually recovers the trace distance property. This kind of desirable trace distance property I was talking about, where you would hope that you could recover the quantum equivalent of the total variation distance. You can't do that with this method. And the other one is that in order for this to be even a semi-metric, not even talking about the triangular inequality, but for it literally to be a semi-metric, you need C to be 0 on the symmetric subspace and positive definite on the asymmetric subspace. This is where the kind of parallels with Shmuel's talk from Monday come in. That this condition, you can do it, but it's an incredibly restrictive condition. It forces you to only be able to talk about a very restricted set of geometries. And so if you're trying to discuss something like a transport cost with respect to a more exotic geometry, it's very, very difficult, or it's not really known how you would find this C obeying these rules to get you a semi-metric. So what's been tried so far? Essentially, the situation we're in is that every kind of existing definition of a quantum Wasserstein distance has chosen one of these desirable properties to sacrifice. So there are a number of really excellent definitions which cover specific cases. You've got the distance that I think Meled will be talking about on Friday. There's a few dynamic generalizations, various distances which do use this kind of coupling method, which have either accepted that you're not going to get a semi-metric, or have accepted that you're restricted to a specific geometry, or have kind of skirted around and modified the definition slightly in order to make it work. One thing you will notice is that none of these really, well, for starters, none of these have any flexibility in the order P. And also, the generality with respect to the underlying geometry is fairly restricted. As far as we can tell, every generalization so far has sacrificed this flexibility in order P and flexibility in the underlying geometry. So the question we ask here is, what do you need to sacrifice in order to recover a definition which is flexible in the order P and in the underlying geometry D? And that's what we try and do here. So for this definition that we're going to present, we start from a motivating property from the classical Wasserstein distances, which is that given a classical Wasserstein distance defined with respect to an underlying metric d on the state space, the Wasserstein distance between point masses or Dirac deltas on x and y is A, independent of the order p, and B, agrees with the distance on the underlying space. So generalizing this property to the quantum setting, we would hope that any quantum Wasserstein distance defined with respect to order p and distance d, that the distance between pure states would be independent of the order p and agree with the any underlying distance you put on pure states. And so this is exactly what we do. Given, I should add, couplings here get a little bit messy, but we will recover them eventually. So we can, between any two states, rho and sigma, we define a quantum transport plan as a set of triples where the way you should kind of interpret this is essentially a set of instructions for how to transport the mass of rho onto the mass of sigma by you take qj amount of state psi j and transport it onto state phi j. And the marginal constraints become these conditions here where if you kind of look at the total amount of mass that you transport, you should start with rho, and the total amount of mass you end up with is going to be sigma. This is where you recover couplings, essentially, in this definition. Any plan Q automatically gives you a coupling defined by this sum over states. It is not particularly obvious that these things exist. I should probably give you an example.
Also, does this has more the flavor of a map rather than a coupling? Or?
Yes. Okay. Yes. So this map, a plan Q gives you a coupling. The backwards map is like one coupling could give you many transport plans.
No, my question was that you said psi j and phi j, but you could also say psi j and phi I in some sense. Maybe
It doesn't matter.
Doesn't matter?
Yeah.
I think like in this case, like we just make sure that rho and sigma are co-spectral, and we just find the eigenvectors. It doesn't matter.
Yeah. The other thing is I should add is that these decompositions are definitely not necessarily orthogonal. This is a very important point of these. The definition of these plans is these do not need to be orthogonal at all. And so you literally just pick up a bit of your state rho and you throw it onto your state sigma without worrying about how the different things you're picking up relate to each other. I should convince you that these things do actually exist, which is, given that we started with a separable Hilbert space, these rho and sigma are going to be compact. So if we write, I'll use K and L. If we write rho in a spectral decomposition, and do the same for sigma, the kind of most natural transport plan you could define between these two is essentially the plan that encodes the product measure of their spectra. So you would get RKSL, this should be an L, amount of psi k, and you transport it onto phi L over K and L.
Sorry, if you actually put a different Hilbert space structure on the two copies of H to make the CJ's orthonormal and the phi J's orthonormal, then does this correspond to just choosing some linear map from one to the other, which is unitary for that inner product, and then for which the partial traces are rho and sigma?
Possibly. The thing is that also I said these phi j don't need to be orthogonal. They also don't necessarily need to be distinct.
Right, okay, now I see it. That was exactly my question. I was expecting this definition more than the other one, but you're not assuming that psi j was the basis with, so you can repeat them.
No, you
Right,
can
so,
repeat them, you can make them not orthogonal. It's not any kind of, there's no structure defined on this decomposition. It's literally just do these Kepras sum up to.
So people have no right to do what I said, which would be to make them orthonormal by yeah.
No, but this, like, for what I'm going to say in a moment, that also, there would be no reason to do that, because then you'd mess up your distance. Like, this is not the key definition here. This is just a definition we use on the way to get to. Go on, Aaron.
I'm not familiar with the notation in the coupling where you have a tensor product in the middle of the bracket.
Sorry, say that again?
Not familiar with that notation in the coupling where you have the tensor product in the middle of the bracket.
So,
Product of two operators.
yeah. If I say,
It's just within the psi j, phi j.
if I write it like this, is that better?
No, he probably just wants it in the same bracket.
Yeah, like there's. Yes. Okay.
Yeah. Or like, you can also, I mean,
Yeah, I like that. He probably wants it.
Yeah.
these are all the same thing. Like,
After we shuffle.
go ahead.
I have a question for this transport plan. So is it the same thing like saying that you only choose your coupling to be separate?
If this sum is finite, then yes. But when we're talking about a generic separable Hilbert space, then not necessarily.
Separable, I mean, is a bipartite state that is not entangled. So it has to take this form. But in general, if you choose a coupling, it can be highly entangled bipartite state. That's something like really hard to deal with.
Yeah.
Here you something somehow reminds me that this is a separable
Yeah.
transport plan.
Yeah.
That can maybe
So-
avoid some technical difficulties.
Yeah. So particularly in the finite dimensional case, we do end up restricting to transport plans that come from separable couplings. You can define them like this for J countable, as we'll see in or countably infinite, as we'll see in a moment. In fact, in the finite dimensional case, any infimum that you care about is achieved at a finite size plan. So in that sense, you are automatically restricting to, in the finite dimensional case, separable couplings. In the infinite dimensional case, couplings with this kind of separate, like partially separable, or like countably infinitely separable.
Is that possible that if you use this kind of separable transport plan, then triangle inequality is not a problem in finite dimension?
We're going to get to that.
That's
Yeah.
Yeah.
Yeah. Yeah. Okay. I should speed up a bit. So, from here, we kind of mirror the classical setting. Given a quantum transport plan, you have instructions for how to transport a pure state onto a pure state, or how to transport rho onto sigma via transporting pure states onto pure states. And so, given that you have a cost given by, I should say, I haven't written it on these slides, but in everything we talk about here, our set of pure states, so the projective Hilbert space we're working on, is equipped with a metric, d. Equipped with a metric that we call d. And this gives the distance between pure states. And so from there, we can very straightforwardly define the transport cost of a transport plan, which is just literally according to the cost function that we put on, which is going to be d to the power p, the cost of transporting the mass of rho onto the mass of sigma according to the instructions given by Q with respect to this distance. Go ahead.
Sorry, do you assume that the metric is induced by the inner product in the Hilbert spaces, or you just?
It can be anything. A lot of interesting examples are induced by norms or inner products, but not necessarily. And then finally, again, as in the classical setting, if you take the infimum, the p root of the infimum over all transport plans of the transport cost, you get the definition of the quantum Wasserstein distance. Go ahead, Spencer.
I was just wondering for D, is there a distance you have in mind? Is that usually just like the regular distance in like a particular basis representation, or is there something more like physics motivated that's like not what you would normally think of?
There are tons that we could think about, and I'm going to talk about some of them. So, what does this look like? What does this construction look like? As long as D is not completely pathological, and by that I mean that D is continuous, and that the 2 norm is Hölder continuous with respect to D, we get a lot of the desirable properties that you would hope for. Firstly, which is probably the most important one, it satisfies the property that motivated it, which is kind of the kind of bare minimum you would expect in the distance between pure states, according to this definition, is independent of order P and agrees with the distance D you put on your projective Hilbert space. It's a symmetric, so it's non-negative with equality if and only if rho and sigma are the same, and it's symmetric. We have data processing where you would expect to get data processing. So in particular, for mixed unitary channels made of unit trees, which are symmetries of the underlying metric on your pure states, the mixed unitary channel satisfies data processing. We recover the kind of natural hierarchy in P that you get from classical Wasserstein distances. That is, if P1 is less than P2, the Wasserstein distance of order P1 is also less than the Wasserstein distance of order P2. It's continuous as long as P is not equal to infinity. I haven't given you the definition of the Wasserstein distance of order infinity, but it's kind of what you would expect, basically, that you just take the infimum over all transport plans of the supremum over the elements of your plan of the distance between them. Very much as you would expect. Sorry? Nope. It's the same as the, like, exactly the same as what you would expect if you were, like, taking the top of, like, the Shatter norms or something. It's just the infimum. Yeah, this is also, like, if you imagine this being, like, the transport cost, this transport cost is the limit as P goes to infinity of the P fruit of the transport cost. So it's literally just the supremum, the same as what you'd expect from any kind of hierarchy of norms you would have. Oh, I've clicked on the screen. There we go. And as I mentioned, when your Hilbert space is finite dimensional, this infimum becomes not in the infinite dimensional case. This infimum becomes a minimum, and it's achieved for a transport plan of size at most 2D squared. So yeah, it's not particularly nice computationally, but it's not infinite. Like if you wanted to calculate this, you'd be optimizing over a space of size 2D squared. Yeah?
Do we know, is that like sharp, like, do we have examples that achieve that? Or is it just like, this is the bound we've got of like how big it could be?
This is the upper bound.
So do you have like examples that like grow like D squared or are that size?
I don't. You should talk to Saroj. about this, but I'll mention this at the end. Yeah, so far, like implementing this, we've not had much success. So this is the kind of last thing here I wanted to talk about. You'll notice here, kind of the list of properties we're missing. There's no triangle inequality here. This is because, as with pretty much every example that comes from a kind of coupling or a generalizing a coupling definition, when you try and get the triangle inequality, you kind of run headfirst into the quantum marginal problem. And we encounter this difficulty as well. We know that there are some kind of pathological distances for which the triangle inequality doesn't hold. We don't know about kind of what conditions you would need to put on D in order to make it hold. And the other thing is, as I kind of alluded to with John's question, the kind of other thing we've potentially sacrificed here is the ability to calculate this. It's very easy to upper bound this distance because the transport cost of any plan gives you an upper bound for the Wasserstein distance, but lower bounding it is a much more difficult problem.
Quick question. So regarding the data processing, to get some intuition, first of all, what would be the distance if you look at a diagonal states? So in the specific case that rho and sigma are like diagonal, or?
That entirely depends on the distance you put on the set of pure states. The idea here is that we're defining a distance with respect to some underlying geometry on your pure states. And so if you pick a different thing for, if there's a different distance between pure states, you're going to get a completely different thing.
Let's say I want just to recover traces, like, even for, let's say I want to recover Hamming distance.
Mm-hmm.
Then what do I get?
I think that is my next slide. No, sorry, I've got 2 more slides and then it's that. Yeah.
But before you move on, so data processing is satisfied for any of such choices? I guess it's...
For any unitaries which respect the geometry that you put on the underlying state space. Yeah.
I see. So for Hamming, is like this unity should be local, etc.
Mm-hmm.
On each case.
Yeah. So we've said that you can't, that the triangle inequality is kind of difficult to pass. So what can you do if you like really care about the triangle inequality? Our answer is just to look at the dual setting. So when you dualize this quantity in a very natural way, you get what we call the Lipschitz operator of the Lipschitz constant of an operator with respect to the underlying distance D on the set of pure states. This definition, in fact, if you were to put a P here instead of a 1, you'd get exactly the same thing. And in fact, it turns out that this definition is actually independent of our construction, in the sense that this supremum is the same as the supremum if you were to take rho and sigma to be pure. But if you take rho and sigma pure, it's just the underlying distance on the set of pure states. And so what that means is essentially dualizing our construction exactly gives you what you would define as a natural Lipschitz constant of an operator on your state space, which is kind of a nice way of showing that this is exactly an analogy of what you get in the classical setting. So this kind of shows that this is a very naturally motivated construction. And then we can then define the closely related norm just by essentially taking the double dual of the original definition. So if you dualize the Lipschitz constant we just defined, you get what we call the double dual norm of the quantum Wasserstein distance with respect to distance D on your pure states, which is indeed a norm. And it sits very neatly at the bottom of this hierarchy. It's a norm, so you get the triangle inequality. And In addition, in the case where you're kind of like what Natalia was saying, in the case where your distance d on pure states is induced by a norm, you actually get this kind of sandwiching of the double dual norm between the first order and the norm you started with, which is, yeah, so this just sits very neatly at the bottom of this hierarchy. So I've talked a lot in generality. What does this look like when you look at specific examples in practice? In the first case, the most simple example to look at is what happens when you take the distance d to be the trace distance between pure states. Do we recover the trace distance in this case? For the double dual norm, yes. What happens, this is the distance that Miller's going to talk about on Friday. I should add, another thing that we've tried to do with this distance, with this construction, is use it to generalize existing definitions of quantum Wasserstein distances that are defined with respect to one specific order to generic order P. And so if you try this with the quantum Wasserstein distance defined with respect to the Hamming distance that Miller will talk about on Friday, you do recover, for order 1, you do recover the original definition up to a constant 2. And the final example that we've looked at, which is a kind of slightly more exotic geometry, which turns out to be incredibly interesting, is what happens when you take D to be the complexity geometry defined by Nielsen. So this is, I won't go into in the interest of time, I won't go into the full definition of this, but essentially, if you take D to be a distance on pure states, which almost like directly encodes the computational complexity of transforming one state into another, you get a very neat quantum Wasserstein distance of order P with respect to computational complexity between quantum states. Yeah, and this just allows us to talk about the computational complexity of mixed states instead of just pure states. So to get a feel for how these distances behave, we looked at what these distances look like when you look at random states. The model of random states we're using here is the standard model of random states, where in order to construct a random mixed state on your Hilbert space H, what you do is you adjoin an ancilla A, you take a Haar-random pure state on this bipartite system, and then you trace out the ancilla, and it gives you a random mixed state rho. When H is finite dimensional, the size of the system A you choose determines this distribution and what it looks like. And so here we're just going to look at the case where where H is a d to the n-dimensional space. I should not have used d there because that's a distance. But just imagine this is the we're talking about qubits here. So H is going to be an n qubit space, and A is going to be an m qubit space. So this constant C, which is going to determine the behavior, is the kind of qubit ratio, noting that m does not need to be an integer. So what happens when you have a large auxiliary system? When C is greater than 1, essentially the probability that you have a kind of exponentially small distance between quantum Wasserstein distance between your mixed states decays as just decays as you take n to infinity. Yes, any metric d. The important thing here is that it's with respect to the diameter of the metric of the the diameter of the set of pure states with respect to D. So in the specific cases of the Hamming distance, or the quantum Wasserstein distance of order 1, with respect to the Hamming distance, this becomes significant in terms of decay when your qubit ratio is at least 3, and for the complexity geometry taking qubits, so D equals 2, when your qubit ratio is at least 9. And what happens on the other side when you take this qubit ratio to be less than 1? It's a little bit harder. You can't really talk in as much generality anymore because it's very dependent on the underlying distance you choose. But in the specific interesting cases that we looked at, both the Hamming distance and the complexity geometry, the expected value of the distance between these random states is generally growing linearly for the Hamming distance, which kind of mimics this distance itself has a diameter of n, and so it grows linearly in the number of qubits. It mimics the kind of maximal order of this distance for small auxiliary systems. And you get basically the same behavior for the complexity geometry as well. This equation is quite long and complicated, but essentially what this tells you is that for C less than 1, so qubit ratio less than 1, the probability that your complexity geometry Wasserstein distance between two random states is less than exponentially big, decays exponentially as n goes to infinity. So generally for large auxiliary systems, the distance decays as you take higher and higher, as you take bigger and bigger systems. And for small auxiliary systems, this distance on average mimics the maximal behavior, the diameter of your pure, the diameter of the metric space of pure states you've got as the number of qubits or qubits goes to infinity. Mm-hmm.
I have a question. So for these random results, what if you consider something like empirical random states? You have I random states, and then you take the average and you convert it to something. And how do you consider this? What's the one convergence in this? I think Diploma had a paper about this. But they cannot do this for W1, they can only do W1 local.
I see. Okay. This is not something we thought about, but that's an interesting question. We should maybe discuss this.
There's some hardness there.
Yeah. Okay. Yeah. Thank you. Go ahead.
How does C relate to kind of the purity of your density matrices? If you have a large C, I can imagine you get very big state with very spread out spectrum. For a small C, it's very close to pure.
Yeah. So if you fix H, if you take C to infinity, the distribution converges to a Dirac delta on the maximally mixed state. And if you take C to be 0, you're just doing the Haar measure on pure states, and you kind of interpolate between the two. So for C less than 1, none of the states rho or sigma are going to be full rank. At C equals 1, they're going to be C equals exactly 1. They're going to be full rank almost surely, and it kind of interpolates between pure and almost surely maximally, or like not almost surely maximally mixed, but converging on the maximum mixed state. Yeah. I think in the interest of time, I'm not going to tell you about classical quantum sources, but you should know that I'll perhaps explain this very quickly. So essentially, one of the things you can do with this, which is specific to the flexibility in order P, is to be able to talk about the distance between the outputs of classical quantum sources in the sense of Pth moments. So if you have if you have two classical quantum sources controlled by the same discrete random variable, and you look at and you want to transform one into the other post-output, the expected value of the Pth moment of the distance between these outputs is sharply lower bounded by the Wasserstein distance between their expected outputs. I don't want to spend too long on this, but the point here is that this is something you can only really talk about when you have generic order P.
This is not an inequality if you minimize over all the possible.
This is an equality in the sense that for any rho and sigma, you can find classical quantum sources for which this bound is achieved, for which equality occurs here. Yeah. And the other thing we can talk about is hypercontractivity. So in the classical setting, essentially, hypercontractivity allows you to talk about the noise of an operation by comparing Schatten norms of different orders. So generally, this TA, if you just look here, this TA is a noise operator, this F is a function. Generally, if you didn't have TA here, this inequality would be flipped. But if you put noise in, this inequality flips to the way it is here. And so this ratio between Schatten norms of different orders with noise on one of the norms allows us to talk about the noise that should say in U. This allows us to talk about the noise of an operator. And we can do the exact same thing using these Wasserstein distances in the quantum setting. So we said that in the hierarchy of quantum Wasserstein distances, we know that for P1 less than P2, the ratio between the quantum Wasserstein distances of different orders is going to be less than or equal to 1. So taking the standard noise channel, where with probability delta, you replace your state rho with some omega. This omega is typically the maximally mixed state or a pure state. And with probability 1 minus delta, you just leave it alone. We get the exact same thing. For states which are sufficiently far apart, which we've shown happens in the general case thanks to the work on random states, this ratio is generally less than or equal to 1. But if you put the noise on the bottom, this ratio flips. And so what this means is, for a general channel, if we replace these general noise channels with a general channel N, this ratio allows us to quantify the noise in the channel N. So if this ratio is less than or equal to 1, it tells you that your channel N is generally not very noisy, and if it's greater than 1, your channel's noisy. So what have we done and where are we going? I've given you a definition, I've shown you that it makes sense, and I've told you what you can do with it. Where do we go from here? One of the most interesting questions is, we've looked at a few examples, but obviously this construction opens the door for kind of many, many other underlying metrics D that you could put on your pure states. In particular, we've used this to generalize a existing quantum Wasserstein distance defined for order 1 to generic order P. Can we do this for other definitions? Does it make sense to enlarge those definitions using this construction? Can we get the triangle inequality? Can we get, in particular, applications to mixing kinds of Markov chains, which, as far as I'm aware, have not yet been touched in the setting of quantum Wasserstein distances? This is quite a big one. Some of the work based on the quantum Wasserstein distance of order 1 for the Hamming distance allows you to talk about the complexity of unitary operations, but because that distance is linear in the number of qubits, you can only really talk about shallow depth circuits in a meaningful way. Can we use this construction to kind of extend those results to generic quantum circuits? And the last one is, how can we lower bound this distance? I've said we can upper bound it fairly easily, but lower bounding it is kind of difficult. And in fact, if you're interested in this, you should talk to Saraj, who's been working on this to what appears to be quite a fair bit of success. Yeah, And with that, I will thank you very much for your attention.